work that was really fascinating, and it was really good work, and it was a different way of thinking about things. And I was so happy to meet he and a collaborator of his, Marianne, that I've stayed in touch with them over the past. Naveen did his PhD with Chandra Bhatt at UT Austin, and then his first job he went to McGill, and he was a professor at McGill, and now he's at Florida. And so it's great to have him here. I invited him here like 6 months ago, and we finally got him here. He just bought his first house, so these are good times. But I have to say, he's a really smart guy. You guys were really lucky to have him here, and the talk he's going to give today, I think, will probably be very interesting. It's not one that we usually have in this group, and it's part of the reason I asked him to come. So please welcome Naveen with me.
Thanks, Professor Nimi, for the introduction. Give me a second before I... Okay. So thanks, everybody, for attending the talk. What I would like to do in this presentation is discuss a method that we are developing to understand decision processes which have multiple dimensions within them. So the approach is referred to as a latent segmentation based approach. The idea here is to see if we can explore alternative relationships within a multidimensional decision process. So I'll discuss this in the context of two studies that we did. One was for a commuter train user behavior in the city of Montreal, and the other one is looking at short-term vehicle usage choices in New York, Washington, and Los Angeles. So what I'll do is I'll discuss the first method and probably take a break and have discussion on that. If you have any questions, again, feel free to stop me whenever you have any questions, and I can discuss the math as much as you want or not discuss it as much as you want. Okay? So again, given the current situation in terms of the greenhouse gases and pollution, public transit is a big, it's an important mode. We are as transportation planners and transportation engineers, we're trying to reduce the dependency on the auto mode. We're trying to figure out how we can make more people use the public transit mode. So it is in this context that we are looking at commuter train choice. So again, you would have heard of all of these negative externalities of automobile. So we're trying to, again, Obama has put up the proposals that we have to reduce our GHG emissions by 50% compared to 2008 levels and so on. So for all of that to happen, we need to have less people driving and more people using public transit. So transit mode, theoretically, it's very nice. It's equitable. It has equity. It doesn't have any equity issues, and also you have significant potential environmental benefits. So in this context, what we wanted to look at is we wanted to understand how individuals who use commuter train in the city of Montreal are getting there. Okay, so these are people who like transit because they're actually using commuter train. So, but we found that most of them are actually driving to transit stations. So they're either parking there and using it. So the idea of this analysis was to understand the reasons behind why people who are transit friendly, who are using commuter train in the first place, are not actually getting there by transit or active transportation. So what can we do as transportation engineers to facilitate these transit users to actually be completely car free, at least in their trips? So for this analysis, we started looking at the mode choice. So how are people getting to the transit station? Then we realized people are not just making a mode choice decision. They're also actually making a station choice. So when you have a commuter train station, there could be one station which is 2 miles from your place. There could be another which is 4 miles. But if you know that you can get a seat by going backwards in the opposite direction of your trip, or in the forward direction of your trip to a different station, you might choose to drive and then get there, park your car. It could be because there is parking. Some of the stations have larger parking inventory. So we realized it's not just a mode choice. There is an implicit station choice also within the choice process. So now we have two choices. We have the train station choice and travel mode choice that we have to worry about. Now, it is a potentially simultaneous choice. So you can have the scenario where I choose to drive, because I want to go to a station which is 10 miles or 5 miles away from my place in the direction of my trip, so that I can get parking, and I know that there is higher frequency of trains at that station and so on. So there have been a lot of studies on this area. So we are trying to look at it in a slightly different way than what past research has done. So the first common studies have done were, they looked at mode choice separately, station choice separately, and tried to figure out why are people not driving and so on. So that was the most common analysis initially. The problem with this approach is you're treating two decisions which are possibly interlinked as independent. That creates imperfections in how you model. So it does not account for that interconnectedness. So there were some efforts to model both of them together. These approaches used what is referred to as a nested logit model. Okay, so in the nested logit model, people, all the stations for a particular mode are supposed to be connected strongly than stations by different modes. Let me show that. So for example, in a nested logit model, what they do is you have a implicit hierarchy imposed. So all stations within the drive mode are likely to be correlated. So if I am driving, there is an interconnectedness that is considered within the station framework within that. If I'm using transit, there are other stations which are more likely to be connected, and so on with the active mode. Okay? Now the problem with the nested logit model is that why should the mode be at the top? I mean, why shouldn't people choose a station and then look at the associated choices they have? So I might look at a station which is 3 miles away. On a nice day, I could bike there. But if it's raining, I might consider taking public transit. Or if it's snowing, which happens a lot in Montreal, you would potentially take the public transit or drive there. Okay, so the idea that we have to impose this hierarchy is not really valid. You have to test for that before we do that. Another problem with the nested logit model is there is a choice explosion in the number of alternatives that you are considering. Let's say if you have a choice set where you have stations of 15 to 20 stations are plausible, because depending on where you live in Montreal, some people have access to 10 stations within a 10-mile radius. So they could go to any of those. So what that means is if you have a lot of stations and with 4 modes, the number of choices that you're looking at explodes to 40 or 50 or even 200 in this case. So that becomes substantially hard to manage in terms of modeling. Another issue with this joint modeling process is that you are treating both of them, so you have the mode and you have the station. You cannot use any information of either choices in modeling the other choice. So if I knew which mode you are using, that would help me model my station choice much better, because if you're driving, the choice set is clear. You are able to drive through probably 10 or 15 stations. But if I'm walking or using an active mode of transportation, suddenly the choice set shrinks. It's only 3 or 4 stations. Probably you're not going to bike. If you're going to work, you're not going to bike 25 miles and take that station. Okay? So by using this joint structure, we are missing this information, missing the fact that you could use information from one choice as information in the second choice. Okay. So what we did in this analysis was we hypothesized that even though these two choices are simultaneous, okay, so people make the decision to the mode choice of how to get to the station and station together. But when they're doing that, we're saying that there is an infinitesimally small time where one of them is made first. Okay, so they could potentially say, okay, even in that simultaneity, they're saying, okay, I'll drive today. So because I'm driving, these are my options. Or I'll choose my station today, and because I want to go there, these are my options. Okay, so we are hypothesizing that there's a possibility that even when they're doing this simultaneously, there is a potential sequence. Now, the problem with that hypothesis is, how do we know what the sequence is? In the data, you are not going to ask a question because the survey is already conducted. You usually don't ask people, okay, which did you decide first? I mean, if you could ask that, that would have been helpful. So did you choose the mode first, or did you choose the station first? Okay, but that is not usually available. So if we hypothesize that way, there are 2 possibilities. So you choose mode first and station second, station first and mode second. Now, because we do not know what happens in the actual data set, we can use what is referred to as a latent segmentation approach to simultaneously consider both possibilities. So what we'll do here is we'll probabilistically consider the fact that some people are choosing their mode first and then station, or they're doing the station first and then mode. So you can use a latent segmentation approach where this information which is not available to us need not be required. Okay, if we have it, we can use that. But even when in cases where you don't have it, you can use this approach to understand it. So this is how it would look like. So there are two potential sequences in this process. So in the first sequence, you are doing the mode choice model. Then you're doing the station choice model. Now the advantage of these two sequences is that when you're looking at the station choice model here, you already know what the mode is. So you have information on the chosen mode because you model this first. So because you know what the mode is, you can customize your choice set for the station choice as a function of what was the actual mode used. The same thing happens here. You know the station choice, so you can customize your mode choice specific to station choice. So when I say customize, if I know the station, I can say, okay, what is this person's travel time by car, by transit, by walking and biking? That gives you a more efficient mode choice model than saying, okay, I don't know what the level of service measures are, because it's a function of that utility of how people choose has important effects based on their travel time and so on. Similarly here, knowing that the person drove, I can generate a choice set related to that, and I can have the drive time to the station as an independent variable in my model. Okay, so that's where the advantage comes in. So we are simultaneously incorporating that. So the advantage of this process is we also get an understanding of who are the people who are choosing mode first, who are the people who are choosing the station. So probably we can see that and understand what is more important to some individuals. Maybe we can try to tailor some policies to address that. Okay? And another advantage is at any stage we are only modeling a single choice. We are only looking at mode or station. So the choice explosion of the number of alternatives does not happen. So you can do all of that just as a simple individual choice model. So all the components of each of them are simple discrete choice models. And this approach does not need simulation, so it's easier to implement than other approaches. Okay, so just to give you a brief structure of the model. So for the segmentation, we have a utility structure. So we are saying that for individuals, based on their socio-demographics or other characteristics, they have a propensity to belong to one segment. So either mode first or station second, or station first or mode second. And within each choice, so you have a mode choice model for this, and you have a station choice model for that. Okay. So all of these in this paper take the form of a simple multinomial logit model. So all of these are just MNL probabilities here. Okay, remember that we have to do two mode choice models. So you have to do mode first as one system and mode second as another system. The independent variables that go into this are different from the independent variables that go into this, because in this I know the station, so I use level of service which are specific to that station, whereas here I will have to do a general model. Similarly, here I will do a general model, but here I will do a mode specific model because I already know the mode, so that gives me more information. So these two will be richer than your separate models. And this would be the probability expression here. So this is the probability that you belong to segment 1, then mode, then station. So this is this sequence. Then there is the so this would just be 1 minus PQ1. So because if this is 50%, that has to be 50% in the sequence choice. Then you have these two models for station and mode.
Okay. So it's static in the sense that it's the day you survey.
Yes, okay. Yeah. So the way we did it is this is a one cross-sectional survey that we had.
Ride a bike and it's a rainy day, you could choose load first.
Yes.
But if you're tired and it's a sunny day, you could choose station.
More the data we can do more, obviously.
Yeah.
But yeah, I agree. So yeah, we basically we had the data and then we started figuring out how to address this problem. That's how we came up with this. So just to give you a sense of the data here, the data for our analysis came from Agence Metropolitaine de Transport. So this is the commuter rail agency in Montreal. They conducted self-compiled responses. So they had about 24,000 responses. I'll explain. Unfortunately, we could not use all of them because we did not get level of service files from them. So Montreal is notorious for not sharing data. So we had to generate all of this ourselves. So we generated it with about 4,000 individuals, and we set aside about 10% of the 4,000 for validation exercises to test whether our model is doing well or not. And we also obtained parking data for each commuter train station from AMD. And we also had land use and built environment data at the TAZ level that we used. Okay? So these were the data that were collected in the response, the survey itself. So again, these are very basic information. So we had age, gender, we had whether they are employed or not, we had vehicle ownership, but we only had it as a binary variable. We did not even know how many cars they owned in their household. We just knew whether they had cars or not. So if they had cars, the variable would be yes. If they had no cars, it was no. Okay? And in terms of trip information, we knew the home location. That was very important for us. Then we had the boarding and alighting station. Which station did they board the commuter train in? And what was their final destination? And we had the access and egress mode. So how did they go? So this was this was how we created our mode choice variable using the access variable. And we also knew their departure time. So for the mode choice model, we needed to generate level of service variables. So we needed to generate travel times for all modes and travel times for all stations. So we used a Google Maps based API to do this. So what we did was we gave the mode, we provided the home and station latitude and longitude, and we generated the travel time. So we had to do this multiple times because we had to do for every home and all possible stations and all possible modes. So this is the reason why we reduced the sample from 24,000 to 4,000, because this itself took a couple of months for the student. And Google Maps API, I don't know if any of you used it, it has weird restrictions. So it allows you to do only 100 or so in a day. I don't know if they've changed it in the last 6 months. So we were running it in 5 computers. Every day the student's first job was he gets up and does that and saves those 500 and again goes back next day again. So that's how, so we took us 15 days to get those 5,000 and we said, okay, enough, I think we'll stop here. And all modes, yeah, all 4. So we did the car, biking, walking as one mode, and public transit. Yes, we did it separately for all modes. Yeah. So now, in terms of the station choice, we saw that people are not just choosing their closest station. So now we had a challenge in determining what the choice set is. We did not want, so the entire Montreal region had 50 stations. So we did not want to consider all 50 stations for everybody because again, the level of service information has to be generated for all of them. So we wanted to figure out, okay, what would be a good way to narrow down and identify viable stations. So what we did was we started looking at the data. And we started looking at, okay, if the closest station is, say, X miles, how far out are they going in the data? Okay, so we wanted to find that ratio and say, okay, maybe people don't go more than 3 times the distance to the closest station. So we wanted to find that percentile. And when we did that, what we realized was, the actual distance to the station, closest station matters. If your closest station is only 3.3 miles from your house, I mean the factor could be, I mean I can go up to 10 miles. So the factor is about 100 when I live very close to station. But if I live 5 miles to the closest station, I'm not going to go 50 miles to go to a new trip, right? So we realized we needed to make this factor based on the actual distance to the closest station. So we created different thresholds. Let me show that. So just to give you an idea, so both these have the same ratio. You have a ratio of 3 if you're looking at distance. Again, you'll see everything in kilometers because Canada we have metric system. So this is the same ratio for both, whereas this is potentially likely, this is unlikely to happen. So we created these ratios, thresholds corresponding to distance. So we did one for up to 2 kilometers, 2 to 5 we created another ratio, 5 to 10 and about 10 we created one more ratio. And we used those distance specific thresholds, again obtained as the 95 percentile from the data and used that to determine the viable choices for the individuals. This is the map of so this is the island of Montreal and these are the 5 commuter rails. Okay, so this is somewhere near the downtown region here. So all 5 commuter rails are here and you have the survey respondents plotted as those black dots. Okay, and this is the St. Lawrence River and this is the island of Laval. Okay? So you'll see that, so for example, people, especially people living here, they have the flexibility to go to this line or this line. Okay, so that's where so some of these lines have different frequencies. So for example, this line has maybe a frequency of every 30 minutes. This could have every 15 minutes. So that means these stations have more trains coming to them. So that also needs to be considered in the station choice process. So we created frequency of stations, frequency of trains at each station as an independent variable so that people here, depending on when they are leaving, they can have that choice. some simple statistics. So the drive mode that we are observing in the sample is about 50%. The objective was to see how we can reduce this, or what factors would influence that. And we have a reasonably large active mode of transportation. We have about 25% people are walking or biking to the. In terms of car ownership, we looked at car ownership in relation to the age groups of the individual. So younger individuals are less likely to have own cars, whereas the proportion is much higher for older individuals. And this is the sample status, basically 80% are employed. It's not surprising because it's mostly collected towards the CBD, so most of the people are employed and going towards their work location mostly. And these are the temporal distributions of the individuals. And another thing we did was we wanted to understand the station. So this is where the whole idea for this paper started, because we saw that average distance to the nearest station was 3.6 kilometers, but the average distance to the chosen station was much higher. So that's where we realized, okay, people are not choosing the station closest to their house, and that's when we started investigating the station choice itself as a problem. And we also have the parking information for that. So then we estimated 3 separate models. So the 3 separate models that we estimated was, we looked at the mode first and station second model, then we looked at the station second and mode second model, then we looked at the combined model that we proposed. Okay, so these are the BIC measures. These already account for penalty for extra parameters. Okay, so this model would have slightly more parameters, so there is a huge penalty that is added, and still the BIC for this model is lower, indicating that this model performs better than the other 2 models. Okay, so again, because we developed this as a way to understand the choice process itself, before looking at the results, we would like to show what the segments look like. Okay, so these are the. So once you estimate a latent segmentation model, you can figure out what is the proportion of each population segment. So we found out that 36% of the population falls within this segment of mode first and station second. 64% is station first and mode choice. And we can also do these numbers by specific mode choice. So you'll notice that people who choose mode first are less likely to drive and more likely to use active transportation. So you have 35% of these people using transportation. And here the difference is clear. So people who choose station mostly are driving and less likely to walk. Okay, so we have a clear distinction. Again, the transit share and shared ride is not that different across these 2 segments, but the huge differences come between the driving and active modes. Okay. So in terms of the sequence of choices, what we found were workers choose their mode first because they probably have more control over their vehicles, so they can say, okay, I can drive, I'll choose that, or because their schedule is rigid, so they want to maximize their efficiency. Then in terms of station first, what we found was people who live away from the station, so if the closest station is very far off for them, they choose the station first, then they choose the station. And at the same time, people who leave before 7:30, these people are choosing station. Again, it's not surprising because basically people who leave before 7:30 are trying to figure out where they have more parking, where they can probably park their car. So that's why they're choosing their station first and then proceeding. Again, I don't want to discuss all the results in terms of the models. So what I want to do is just show some differences. So you'll see that for the same variables that we have in both models, the coefficients, again, you should not really compare the coefficients, but it shows you the magnitudes are different, and in some cases, you'll see even the signs are different within these 2 models. Okay. Now here are the level of service measures. So we have here the average travel time to viable station. So when we are doing mode first, we do not know the actual travel time. So we are looking at average of all travel times to viable stations. Okay. Then in this, when you're doing the mode second, you already know the travel time to the chosen station, so you can consider that as a variable here. Okay. So again, this is the advantage of this system where you'll get good variables for at least one of the 2 models that you're developing. To give you an example, this is again another variable which varies. So this is an example of a variable where you have negative coefficients in one, positive coefficients in other. So it shows that some of the variables, depending on when they are being considered, have opposing effects in the choice process itself. and this is the station choice. So when you're doing the first as the station choice, so on the right, you'll see that travel time obviously makes a difference. The more is the travel time, less is the likelihood of people choosing that. But then if you have the chosen mode, so because we already know the mode, you can better calculate the travel time impact for the user. So we have these variables that capture that. And train frequency, as you would expect, the more is the frequency, more people are going to choose that station. And also parking has an expected impact, where you find that more parking that is available, it increases the chance that people choose that station usually. Now, after we estimated the model, as I said, we had 10% of the sample left aside to check and validate. So here what we did is we predicted the log likelihood. So we predicted the probabilities and just computed the log likelihood measure. And we wanted to see how the two separate models were performing relative to our model. Okay? So you'll see that lower negative is the better here. So the closer the number to 0 is, the better it is. So you'll see that all for different segments. So we did it for the full sample, it's substantially better. So this was the full sample size. Then we looked at different segmentation. So we looked at only for males, only for workers. So you'll see that these two will keep flipping. So in some cases this is better, in some cases that is better. But overall, the latent segmentation model is substantially better for all of these cases. Okay? Again, probably these are too small samples to compare, but still the general idea was to show how different samples performed in terms of the model estimation. Okay. So then what we did was we went ahead and conducted some elasticity analysis to understand how each factor will influence the process. Okay? So we looked at gender. Again, this is not something we could change, but just to see that we found that men are actually using more transit in the region. Okay, so it's possible that the women are driving the cars probably because they're taking the kids to work, daycare, and so on. So that's something we found. Then we looked at how the increase in car ownership will impact the process. Okay, as you will see, it has a substantial influence. So if people own cars, they are very unlikely to use transit. Okay, so this could be an interesting point where we can probably already in Quebec we have slightly higher taxes on car ownership, but probably that's something that can be looked into in terms of improving maybe benefits for using public transit if they are provided, that might reduce car ownership in that sense. And we also looked at travel time, because this is something we can control. If you improve the public transit system, that the feeder routes connecting the homes to the commuter trains, we wanted to see if that would be beneficial at all. And we found that if transit time reduces by 5 minutes, you will see a jump in the transit share. We also see that if you improve drive time, that will further reduce usage of transit. Okay, so the reason we looked at this specific drive time is they're improving the freeway system in Montreal. They're expanding some of the lanes, so that will actually affect this substantially in reducing the number of people using transit. So whenever you're doing policies of congestion mitigation, this is something we should look at, because if you add lanes or increase capacity, you will have more people driving, and that will negatively influence transit. I think the current situation of transit in the United States is potentially because of that reason. We built more roads, so even the people who are using public transit realize they can do an efficient job driving, and to a stage where public transit in most urban regions in the US has become a losing venture. Okay, so yeah, and one more thing we found, as we would expect, is if you add frequency in terms of number of trains arriving at that station, that also had a positive effect. So we found that in terms of transit agencies, they would have to figure out how to improve connectivity to the commuter rail system. So which new rails or new bus lines or improved frequency in the bus rails might help people from switching from driving to the commuter train station to moving towards a public transit system. Okay, so that I'll include this. So again, just to recap, we looked at how individuals were looking at commuter train choices. The two choices we looked at was which station to go to and how to get there. Those were the two choices that we explored. And the idea of this was to understand how transit ridership varies. So now we can use this model to predict how transit ridership in the entire urban region changes. So without such models that capture the underlying behavior, you will end up with estimates which are either over predicting or under predicting the impact of policies. And we found that compared to the traditional models, we have an improved explanatory power than the previous research. And also the elasticity analysis confirms what we did. The validation analysis clearly shows that there is substantial improvement on a holdout sample of how our model was predicting both station choice and mode choice. So I'll take a quick break and ask if you have any questions. If you do the same analysis, you'll get a negative sign of all of this. It will just be opposite. So the way to do elasticity analysis for a dummy variable, which is a binary variable here, is we are imagining a situation where all men become women, all women become men, and then look at what they will do, and we'll run that probabilities and compare it with the base case. That gives us the change. So if I do the same analysis for female, it should give you all the negatives will become positive and positives will become negative. The magnitude might be slightly different because this is percentage change compared to how many people are driving, the percentage change. So if you do this, the signs will all be negative. The magnitudes will be slightly different because men and women are not 50% in the sample. So but the result will not change. If the variable was significant, you could not say that mode choice is independent of the model. Right? If the variable came significant in the model, that tells you that the variable, if it is independent, all of those should be zeros. If the variable was not affecting the decision process, elasticity analysis will pick it up. It should give you 4 zeros here. Because it's not zero, it clearly tells you it's not independent. We did not have that data variable. That we did not have a lot of information on the respondent. We only had their age, employment, whether they own cars. We did not have any information on the household composition. We did not. It's a variable that we would have tried if it was there. No.
How are you coming up with one node or one station to feed into the next?
No. So the way it is done, okay, let me explain that. Let me use this. So what we do here is, so if the individual belongs to this segment, okay. So again, remember, we are not completely allocating an individual to any segment. We are probabilistically allocating. So what that means is, an individual, because of his or her characteristics, might be 80% likely to be here, 20% likely here. So if you are here, okay, when we are here, conditional on here, I will model the mode choice. Okay, in this, I don't have any information on the station, I'm just doing the model. Now, because I'm saying this is the sequence, when I go to the station, I already know the mode. So it becomes an independent variable in my system here. Mode becomes an independent variable in my system because, see, for estimation purposes it will be confusing, but if you are predicting, I would have predicted my mode at the end of this model if you are looking at a sequential model. So once I know my mode and I use this to determine my station. Okay? I'll do the same here. Now, unfortunately, I don't know this share, so I have to wait with that share to both. That's why I have to compute this probability, all 4 probabilities for every individual have to be computed. Okay, and appropriately weighted by their share. So if they are 20% likely to be here and 80% here, this probability will get a 20% weight, this probability will get an 80% weight. And that is determined by the maximum likelihood estimation. So you maximize the log likelihood. For each person, we'll get a different share. What I showed you are averages across the population. So I'm not saying that every individual is only 36% here and 64% there. It's the average of the entire sample. So some of them might be 95% here, 5% there, and vice versa, and so on. But yeah, but you are recognizing that mode choice is already done once you come here.
Follow-up, so maybe
Looks like cheating, right?
clarification.
Yes.
Sequence choice isn't models. You're basically putting each person through both sequences and estimating which one is maximizing.
Yes, yes and no. That's what I am doing.
Yeah.
But if the sequence itself was not, if one of the sequences was correct, okay, if the people are not using both sequences, if everybody is making a decision using one sequence, the single sequence model that I estimated where I looked at station 1 and mode 2 should outperform this model. Because this model has extra parameters. Remember, if you're doing this segment or this segment separately, I'm only estimating one mode choice model and one station choice model. Now by doing this, I am exploding the number of parameters. I mean, not exploding, but I'm doubling the total number of parameters because I have a model for this. I have an extra mode choice model, an extra station choice model. That's why the BIC becomes very important. You cannot compare log likelihoods. This will surely have a better log likelihood. So you have to penalize for extra parameters, and then that's when we're doing it.
Yeah, but I think what we're confused on is the top sequence choice model.
Okay.
That's, I think, I may be taking words out of your mouth, but
I don't want to derail you. I don't want to derail this from getting to the next part, but I'm still a little confused. So you were talking about the nested logit model, right? And basically you have these exploded alternatives because it's still probabilistic. When you do the first node choice model, for example, you're still getting probabilities for each mode.
Yes.
So how are you selecting that mode?
Okay. See.
That's my question.
So see, I am selecting that mode only for estimation purposes. Okay. The reason I am selecting for estimation purpose is when I come to this model. It's a very good question actually. So when I am looking at this station model, if we agree with the hypothesis that station choice is secondary or after mode choice, when the person is doing the station choice, do we know his mode or not in the data? If this sequence is imposed, right?
Got it. Okay.
So if the sequence is imposed, I know the mode.
Right.
So that's where the advantage in these two models come, because these two models perform much better than these upstream models. That's where the improvement in the data fit comes from. Because when I'm doing the station model, I know the mode.
Got it.
Yeah, that's what we are exploiting. So now if you want to use this for prediction, okay, if you're using this system for prediction, what we'll do is we'll run the sequence model and you'll generate a random number. So let's say it is 40, 60 probabilities. You generate a random number. Let's say it's 0.2, less than 0.4. So this is the chosen sequence. I don't do that again. I'll leave one of them. So then I predict my mode.
Okay.
I choose one mode. I know the mode. I predict the station choice. That's all. So that's how you'll use it for prediction. But when you're estimating, you have to use the way I'm talking
Makes
about.
total sense. Thank you.
Yeah, transit, active, shade ride, and drive. So driving or shading. Here, they won't be taking another train line to take another commuter, because once they are on the commuter train, they can go to downtown. So we are only using bus as our transit system. Yes. And maybe. Yeah, there is a metro line, so we were not, again, the data had transit or not. So we did not have, but there could have been metros. So people could have taken metro to some distance, but that would be near the central business district. Most of the individuals are coming from the suburbs, so they wouldn't have access to metro. Metro is only on the smaller Montreal island. It's not there in the rest of the. Yes. But yeah, there is a possibility that some of them might be using a metro mode, but we don't have that information. We did not consider it.
your implications of,
This one? Okay.
yeah. I think that's really, did you see if there were differences in the mode choice first versus station choice first by the geography? Like, were there certain region where people were choosing the mode first? And if you did, why do you think that would be?
Yeah, so in terms of spatially, we did not do exactly what you are asking, for sure. But what we did find was people who are closer to the station actually ended up using the mode choice first, because I mean they know they have a station close by, so they started looking at mode as a more variable option. But yeah, we did not look at the spatial analysis of it.
Okay.
Yeah, again, there won't be too many differences in the sense that most of these are suburban users, because commuter rail comes from very far, like some of them run from 25 miles long. So all of them are mostly suburban users, because Montreal has a very good bus system and a very good metro system. So within the island of Montreal, nobody will use a commuter train because it's expensive, less frequent. Okay, so we are looking at a reasonably homogeneous sample, but there could be differences. But yeah, we haven't examined that. Yeah, there are some. That's something we can look at.
Interesting to know that 34% that came from, yeah, did it come from neighborhoods that were more sort of geared towards alternative modes, or
Yeah, that's something. Yeah, but that's so. As you'll see, there are very few people in this part of the system. Most of this part has metro access to it. But yeah, that's something. Yeah, we have to look at. Yeah. In terms of if there are spatial differences or it's uniform, we'll have to look at that. Yeah, there might be pockets of.
pockets of like I'm thinking those pockets where everybody wanted the one-way street to go to different.
Yeah, that doesn't have commuter rail access, right?
I
That
know,
just
but I
does,
mean,
yeah,
that-
yeah, but
that's
there might be,
neighborhood.
yes, yes,
Yeah.
there might be, yeah. I think we were thinking about all suburbs are similar kind of setting, but probably there is some suburbs which are actually more bike friendly and encouraging that. So that's something we'll have to explore. That will be, yeah. Like for a city which is covered with snow for like 6 to 7 months of the year, the amount of biking you see in Montreal is phenomenal. I mean, it's we have a Bixi system that's been running now. We clock 3 million trips a year, and there very high rates of usage, and most active bikers look down on people using Bixi because it's not a nice, comfortable bike. And even with Bixi, there are a lot of people who use. I mean, I've seen people biking when it snows. I'm barely able to walk on the street, and you'll see people go by at 20 degrees. It's nice. I mean, now there's a lot of issues with safety also that are coming up now because of a lot of increase in biking, and they have a very good bicycle lane, cycle track facilities. So it's a very interesting city that way. No specific reason. We found parking to have a positive effect, and I thought we just identified some scenario. Yeah. So if you reduced parking, that's something we should have tested. I don't know if I removed the table from the cells. Yeah. Did I test? No, I don't think we tested it. Yeah. That we could test whether increasing parking and decreasing. I think increasing parking will increase the drive mode. We have 200 right now. I think the reason we did not do it is parking has 6 categories, so we would have to run 5 elasticities. Probably the student did not do it. This is a master's thesis from one of my students. Yeah, I missed that. Even in Montreal they shut it down. So the bike share system is only open from April to November. Okay, and it snows in April, November also, but we still have few number of bikes. But even when there is no Bixi system, there are bikers who have their own bikes who are biking all the time. Yeah. I mean, we saw that we did some work on the bicycle sharing system data there. We clearly found people are not using that system as much in April, even May. June, July, when it warms up, that's when the demand increases. So as a private company, it makes sense not to keep them on all the time. And people, in the snow, if there is bicycle racks taking up space, people complain a lot because they don't get parking. So they don't, when it's not being used, they try not to keep them on the side. No, that would be a different problem, like Atlanta, right? The second part of the presentation, what I want to do is we are using a similar approach, so we just tweaked it a little bit to for a specific context. So I'll just explain that. I'll probably not go into as much detail as we did in the other one. So here, what we are looking at is short-term vehicle usage decisions. Okay, so typically, again, in terms of the transportation mode, greenhouse gases and all of that, again, it's the same reason why we look at vehicle ownership. So the number of cars owned, the mileage that individuals drive or households drive has a significant impact on what contributes to our GHGs from the transportation sector. Now, the traditional literature on vehicle ownership has focused on long-term usage decisions. So they look at, okay, how many cars do individuals want to, households want to own, and what is the mileage they will drive in a year. Okay? But an important fact to recognize is the mileage that individuals or households put on their cars in a year do not magically happen. They are cumulative additions of what happens every day. So there are daily decisions being made on, should I use my pickup truck to go somewhere, or my SUV to pick up my daughter, or to drive to work in my sedan. So all of these decisions then add up to your cumulative yearly usages. So what we wanted to do is we wanted to start exploring how these short-term decisions are made, because these short-term decisions are important if you're using an activity-based model to understand the spatial distribution of emissions. So if you do not know how many miles you're doing on your sedan or your SUV on a particular day and at what time of the day, you will not get a good picture of where the emissions are being produced, where they are being emitted, and how the emissions are spreading in the region. Okay? So that's why only recently there have been papers that are moving towards, okay, we have a good handle on the annual outputs. So those could potentially serve as control totals. I mean, if I know that I usually use my sedan for 15,000 miles, I'll probably use it every day. But they don't provide you the exact picture of the spatial distribution of how mileage happens in the urban region. Okay, so that's the reason, main motivation for what we are doing this. And one more thing that we wanted to explore is what kinds of purposes drive what kinds of cars. I mean, are people using for commuting mainly only sedans, or maybe if they have to drop their kid off, are they using pickup trucks? Maybe basically to understand how we can tweak that behavior to bring everybody to lower emission-based cars. So even in this, you can think about a dichotomy of choices. So you have individuals every day making this decision of what kind of car to use. So we are looking at households which have different types of cars. We are not looking at households who only have one car. We selected some households which have different mix in their vehicular distribution. So they have a sedan, an SUV, pickup truck or van or something like that. And we are trying to figure out what car are they choosing. So do they use their car on that day or not? And how many miles are they going to use that for? Okay, so here again, miles will serve as a surrogate for location. Ideally, we would like to model location, but location becomes a spatial problem and becomes slightly more challenging to understand. And not only that, but you have multiple locations in a day. So how do you model all of the if I make 3 trips, I have 3 locations. So simultaneously modeling the vehicle type and 3 locations becomes complex. So what we'll do is we just aggregate the mileage from each location and create a total location that you're in. So it gives you a sense of how many kilometers am I using my car for within a day. Okay, so that's the second choice. So just as we talked about in the previous case, we can imagine that people choose the car first and decide where to go later. Or they can say, okay, today I have these activities, so I'll have to travel about 80 miles. So probably I should take the smaller emission car or the smaller fuel emission car. So again, we have the same relationship in terms of the choices that we have. Okay. So what we did here is, with this idea, we started looking at the 2009 household travel survey. We started looking at the New York region, hoping that there will be variability in terms of how things happen. Then we started recognizing that, okay, we can potentially do it for multiple cities. Why only restrict ourselves to one city? So we started looking at New York, Los Angeles, and Washington. The idea being that this is probably the most public transit friendly system, in somewhere in the middle and the lowest public transit options in the region. Okay, so we wanted to see how this affects the behavior among individuals and how these patterns change. In terms of the sample, it's actually very surprising to look at this sample. But remember, these are people who are actually using their cars. So these are not. So if you remove people who use public transit from the data sample, maybe the driving behavior across cities is not that radically different. Okay, so we are looking at the sample here. So okay, this is just the number of males and other details. So let me look at the more interesting ones here. So if you look at this statistic here, we are looking at number of people who use all their cars. Okay, so if they have 2 cars, they're using both of them. If they have 4 cars, they're using all 4 of them in a single day. So this is the proportion, and you'll see that New York has the highest percentage. I mean, it's potentially possible that they have smaller vehicle fleets, so they only probably own 1 car and they use it. But this shows you that maybe because parking is more expensive, they don't want to own a car and not use it. So that could be one of the factors here. And Washington DC has the low, so they have multiple cars in their household just staying there most of the time. And at least some subset of the vehicles is this. Then we are looking at the distance here. We found that Washington DC people use their small cars longest. SUVs have the highest mileage for the New York region. Again, there are differences across cities on how they use their vehicles. You'll see that in none of the categories, only for the truck category, Los Angeles actually has higher value. I mean, you would expect Los Angeles for the people to be driving much more, but it's not, because again, these are self-selected individuals who live in New York and Washington and choose to drive. So they are usually driving more than the rest of the population. And then this is the distribution of vehicle types. Again, very close. You have 43% or close to 44% of auto. And then SUVs, again, you have much larger SUV proportion only in New York. Washington has lower, and Washington has a large number of trucks. So the approach that we are using is exactly the same with a minor change. I'll explain that. So we are looking at the latent segmentation. We have vehicle type. Now the difference comes from here. You have mileage, which is a continuous number, so you cannot use a multinomial logic system. We are using a linear regression based system here, and the model system would look like this. But one difference in the data here is we have 3 cities of data. So within each city, there are unobserved factors that are common to people from that city. So we have 3,000 people from Washington DC. All 3,000 people share something common. They share something about the city, the culture, that cannot be examined purely with observed attributes. So we need to recognize that. So the current system that we developed, it does not recognize this. So what we did was we created a scale variable which is specific to each urban region. Okay, the scale variable captures the differences. So you fix one of the scales to 1, and you compute scales relative to the Los Angeles region and the DC region. So the scale is a function of attributes corresponding to that city. So this captures unobserved factors that scale the utility. So for example, a utility of 20 in DC need not be same as utility of 20 in the other region. So for that reason, we have to account for this. So this was the mathematical difference that we made. So we are accounting for scale here in the discrete choice probability. So in the previous example, this term was 1 because there was only one region. Here, because we have multiple regions, it is 1 for one region and estimated for other 2 regions. So we can exactly capture the differences across the 2 for the 3 urban regions. Same thing in the linear regression. This would have been 1 if it were not there. So here it will be 1 for one city and then captured, estimated for the other 2 cities. Okay. So this is how the scales are parameterized in both cases. Theta, you can, again, the scale need not be a constant, it is a matrix. So you can have different variables affecting the scale. Same thing here. Okay, you can have different variables affecting the scale. Again, this is something that we use a lot when you're looking at multiple waves of data. So for example, in some cities, somebody was mentioning, you have a travel survey every year that is conducted at UC Davis. So something might change from 2007 to 2008. So for example, this building was built recently, so there is more travel happening to this part of the campus which was not there in the past. So that can be accommodated with the scale. So that will allow you to differentiate something that has changed, that is common to everything that happens in that year. So that's the reason why we capture this, especially when we are looking at research where collecting panel data is becoming very complicated because of the people don't continuously fill the data. So if you have multiple cross sections and you capture the scale, you are as good as getting a panel data. You don't have the same individuals, but same behavior is repeated across the year. So if you're looking at vehicle ownership or vehicle mileages, all of those behavior are the same. We can do analysis using the scale in terms of these factors. Okay, so that's the advantage of using the scale-based approach, and the probability expressions and all of those will look exactly the same with just this parameter to be estimated. So we estimated several models. So one was the same distance, vehicle type, distance, vehicle type, two separate models. So vehicle type affects distance, and then we added scale parameters. And you'll notice consistently, whenever you add scale, the log likelihood substantially improves. The reason being, people are similar, that once you accommodate for that similarity, you improve the fit. Okay. In terms of the latent segmentation model, again, the latent segmentation model outperforms all independent models, even with scale. So this is how it performs. And as you'll see, I did not show these numbers in the past, so you'll see that you'll estimate substantially more number of parameters when you do the latent segmentation. So if you have an individual, only one part of the segment, you have only 104 parameters, but you end up with 128 when you estimate the latent segmentation, because you're trying to do twice the number of models when you do the latent segmentation. Okay. And then we estimated the latent segmentation model with scale. For this specific study, we found that the extra 12 parameters did not yield as much benefit as we would expect. So the latent segmentation, I mean, if you look at the BIC values, you could have just gone with the simple latent segmentation model. Again, we just wanted to see there is an improvement in the log likelihood, but the penalty imposed because of these 12 parameters was not enough to warrant this. So we just used this model for our discussion. So in this case, we had a lot more variables that were important in affecting the sequence choice, depending on where you live, which city. You also have gender. So the reference alternative is distance first and vehicle type second. So these look at utility for vehicle type first and distance second. Okay, so you are finding that men prefer to choose their vehicle type and then decide on distance. So they choose, okay, I want to drive a pickup, and then decide how long to travel and so on. Again, flexible work schedule allows you to choose that. Again, same thing, no fixed work. Depending on part-time employment, all of these attributes. Again, some of these attributes will be hard to hypothesize. It's not like we know how these should behave in terms of these choices. So we let the model inform us of the relationship. I mean, I wouldn't have guessed that this should be positive or negative upfront before running the model. So then we looked at the allocation for each segment. So you'll see that these are the segment shares for the first segment. So this is vehicle type affecting distance. So this segment is about 22% of the sample, and you'll see that the mileages are substantially larger. So these are people who choose their type of the car first and then choose the mileage. And it makes sense that because they are driving so far, they have a clear idea of their fuel efficiency of whatever car they use. Okay, and mostly this is dominated by auto. Okay, so these are people who say, okay, I'll use my sedan, I'll put a lot of miles. Okay, if you look at the second segment, this is about 70, so it ranges from 78 to 75. Here you see the average distance is much smaller. You only have about 25 miles. So here, it's not surprising the share of auto drops. Okay, you have higher usage of SUV. So this is the segment where the distance is determined first and then vehicle type is determined later, and you can clearly see the intuitive differences across the population segment. So if you have such wide differences in kind of distances traveled, if you consider only one kind of relationship in the model, you will end up with a very substantially wrong analysis. Okay? So some major results from the outcomes. So we found that increasing distance usually makes them choose either auto or van, while decreasing the probability of SUV. And we found that in the vehicle type distance structure, the actual distance was not affected once they choose the vehicle type. Okay, so again there were some differences in how the first variable affected the second variable. In some cases, the first variable did not affect the second variable. Again, that does not rule out the possibility that these sequences exist. That it is possible that this latent segmentation not only captures this causality, but it could generally be capturing inherent population heterogeneity. So variation that exists among people. So we might not be capturing the exact segments that people have, but we are still capturing more variability in the each independent variable in affecting the choice process. Okay? And we also found reasonably significant scale differences in some cities, but some cities did not have a lot of difference. Okay? So to conclude, in this case, we developed a scaled latent segmentation model to analyze vehicle type, distance, and distance vehicle type. And again, this introducing the latent segmentation substantially enhances the model fit, and because it accommodates for heterogeneity, and it identifies interesting behavioral patterns in sample. So again, this is not to say that there aren't limitations of these studies. There are substantial new things that we can do. Here we are imposing the idea that there are only two causal structures. So we are saying A, B, B, A. But there is a possibility of a segment of population who are capable of making the simultaneous choice. So we can potentially have a third latent segmentation, which is AB, or they only look at A and B independently. So we could add, that would only balloon the number of segments. So we could have, instead of having 2, we might have 4 segments. So there is a segment where A follows B, B follows A, then A and B are completely independent choices, then A and B are completely simultaneous choices. So we could look at that structure also. Again, that would become even more trickier in interpreting the model. That will be a challenge on how to do that. That's something you can do. And also, we are doing very simple models within the sequence. You could consider heterogeneity, unobserved heterogeneity, and look at more complex structures within the systems for each choice themselves. Okay, so with that, I just want to acknowledge some of the people who worked on these papers with me. Vincent is a master's graduate. Interesting story is the Ministry of Transport Quebec never wanted to talk with me. We tried to set up meetings with me, but the moment he graduated, they hired him. So at least that's I was happy with that. Then this is my PhD student who's working with me at McGill still, and one of my collaborators, Karthik Konduri, who's an assistant professor at University of Connecticut. And my website has the papers that I talked about. These are the 2 papers, and I have my card if you want the link to my website. And thank you so much, and I'll be happy to take any questions. Yeah, when we say short term, I totally agree with what you're saying. When I say short term, we mean the decision of using it in that day. So to get daily mileage and daily usage, that's the only idea. We are not in any way saying that the decisions are made in the short term, probably, but at least they have some flexibility to change. It's not like an annual decision, right? It's not fixed. It can change, but in some households, the husband gets the sedan, wife gets the SUV. It's done. The whole year, that's how it is. So that is something that we are not able to find data that has multiple days of information. So we want to see if there is repetition, like you're suggesting, or switching happening. Within a day, we found very little switching. So I pick a car. Most of the people, 99%, are using the same car in that day. There is a very small sample of 1% who switch. We're trying to see if it is large enough to do some analysis on it. But initially, that was the idea with which we started this paper. We wanted to figure out switching. Who are people who switch, and how are they making that switching? And then we realized that's not a viable analysis, at least as of now.
People that drive together, and
think we considered whether whether it is a joint travel or not as a variable. So if it's joint travel, then even then there still is a choice, right? You could have chosen your SUV or a sedan. So that comes into the picture in terms of choice of them. So when it's joint travel, we've noticed the bigger cars being picked. So SUVs are preferred if you have access to them. Again, all of these models consider vehicle types only that are available to these households. So if you don't have an SUV or a pickup truck, those are automatically excluded. So they all have at least two types, and we are carefully allowing only for those choices in their process. Yeah, but we have joint travel as as an independent variable, but there is clear endogeneity there, and there can be more sophisticated ways of capturing that case. Yeah, I have a card here, so if you want a website or something, you can go there and you can. There you go.
So I can. Yeah.
I told Aaron as well. I did.
Walking, but not for biking. Yeah.
Not even moving in that direction. There's no kind of authorities to have. Way down. Hopefully they're like shifting it. Right, and my apartment mate. Watch out for getting run over by a bike. Yeah, downtown also.
Anyway, I'm not going to get over that. There yet.
Wow. All right. So I'll be back.